All right, we have some practice problems on conversion and density. Our first two steps with this conversion are to know what amount we're converting, which is the 57.5 ounces, and then to be able to write these relationships as conversion factors. The first one we're going to use is this one to get rid of ounces, and then the next one we use is this one to get rid of pounds. So the ounces cancel and pounds cancel, and we're left with kilograms. This is the answer the calculator gives me. Looking at the significant digits, we have something with 3 significant digits, something that's exact, and something else with 3 significant digits, so we need to keep 3. And this becomes 1.63 kilograms. For this next problem, we want to convert a certain price, euros per 100 grams, into dollars per pound. Let's go ahead and use this conversion factor for the euros to dollars first. Then we can use this one for grams to pounds. So with these two conversion factors, we've canceled the euros and we've canceled grams, and we are ending up with dollars per pound. Our original amounts, we only had 3 significant digits, and then 3 significant digits and 5 significant digits. So we should take this to 3. So it might look a little bit different to have 3 significant digits in this dollar amount. We're just saying that given the rate, we know this to plus or minus 10 cents, not to the closest penny, but better than the closest dollar. This next one is another conversion where we have 2 different units. So this is a relationship, and we're trying to convert that relationship from meters per second into miles per hour. So this first conversion factor can be used to cancel meters and start talking about miles. Then I want to stop talking about seconds, so I'll use this conversion factor that there's 60 seconds in a minute and 60 minutes in an hour. And then at this point, meters have canceled, seconds have canceled, and minutes have canceled. We have miles per hour. So my calculator gives me a lot of digits. This time I just kept the 10 to the 8th because the rest of this comes out to a term with the decimal point in the correct place. And then our significant digits, we have 3, 4, and then infinite. So we should go to 3. So this makes 6.71 times 10 to the 8th miles per hour. So this conversion is again something with 2 different units, a relationship, a density, that we are going to keep as a density, but this time the relationship will have kilograms per liter. I've written some metric relationships below. Let's go ahead and use this one to convert grams to kilograms, and this one to convert milliliters to liters. So now our grams have canceled and our milliliters have canceled, and we will have kilograms per liter like we wanted. So I just grouped the powers of 10 together over here. 10 to the 3 times 10 to the negative 3 ends up as 10 to the 0, which is 1, so this cancels, and we still have 19.3 as our density in kilograms per liter. And then the significant digits just stay the same because we have 3 to start with and just multiply it by things that are exact. So we end up with 3. So for this one, we're really trying to convert a meter cubed into centimeters cubed. We're trying to figure out how many centimeters cubed we have if we have a cubic meter. So here are some relationships between meters and centimeters. A centimeter is 10 to the minus 2 meters, or there's 100 centimeters in a meter. So we have this conversion factor, 10 to the negative 2 meters on the bottom and centimeters on top. If we only used it once, we would only cancel one of the meters, and we would end up with 1 meters squared centimeters over 10 to the negative 2. And so our units would not yet be cubic centimeters. So what we need to do is either cube this conversion factor or use it 3 times, whichever one is easier for you. When we do that, we have canceled meters cubed. We've canceled meters 3 times, and we end up with our cubic centimeters. So combining our powers of 10, 10 to the minus 2, 3 times gives us 10 to the minus 6. Since we have 10 to the minus 6 in the denominator, this really equals 10 to the 6 in the numerator. So a cubic meter is 1 times 10 to the 6th cubic centimeters. Or if we write this in regular notation, it would be 1 million cubic centimeters. This is another problem where we have square meters and we are trying to convert to square feet, and the relationship that we have is just a regular length relationship of meters to feet. So if we multiply this amount of square meters that we're trying to convert by the conversion factor just once, we cancel meters once and we end up with meters feet as our units. We don't want that, we want square feet. So we either need to multiply it by this conversion factor a second time or square the conversion factor, effectively the same thing. When we do that, we cancel both meters, so meters squared are canceled, and we do end up with feet squared. Then our significant digits here are 3, so our area is 30.9 square feet. So this problem here is trying to convert cubic yards to liters. Given our relationships over here, it looks like we can take cubic yards to cubic inches if we use this 3 times, and then we can take cubic inches to cubic centimeters. Then we have this relationship over here relating cubic centimeters to milliliters, and then that is a metric conversion to get to liters. So here is our game plan. To get to cubic inches, we are going to need this conversion factor 3 times, or cubed. And then we also need this conversion factor cubed. Then once we have cubic centimeters, we effectively have milliliters. And then we can get from milliliters to liters with this metric relationship. So here the cubic yards have canceled, cubic inches have canceled, cubic centimeters have canceled, and milliliters have canceled. Then for significant digits, we started with 3. We multiplied by a lot of things that are exact, so we should end up with 3. So this would be about 1,720 liters. In this problem here, we have to calculate the density, so we need the mass over the volume. We have the mass. Instead of being given the volume, we are being given some dimensions. For this rectangle shape, we just need the 3 dimensions multiplied together. This ends up being 55.89 cubic centimeters. It should only have 3 significant digits though. I'll keep these, but just underline this to show that. So when I do this density calculation, we have 4 significant digits in the numerator and only 3 in the denominator. So it comes out to 4.70925 and so on. We'll round this to 3 significant digits. And so the density there would be 4.71 grams per cubic centimeter. These two problems are very similar. The difference is the number of significant digits you can keep in your answer. Again, we're calculating the density using mass over volume, and we know the mass. This time we don't exactly know the volume. We're being given the volume by liquid displacement. A certain object causes a water level to rise from 18.5 to 35.6 milliliters. So that difference that it made is the volume. These graduated cylinder readings can be taken to 1 past the decimal. So this is where our uncertainty is. So we can keep 1 past the decimal in our answer. Now that we're doing division, we can look at the number of significant digits. Something with 3 divided by something with 3. That means that we can take the answer that we get and round it to 3 significant digits. This density would be 2.67 grams per milliliter. So this one, again, we have the mass and the volume is being given by liquid displacement. So we want to know the difference in these volume readings that was caused by the volume of the object. And again, the graduated cylinder readings are only known 1 past the decimal, and so our volume is just 1 past the decimal. So this results in 5.84 grams per milliliter. But with the division here, we're dividing something with 5 significant digits by something with 2 significant digits. So we really should only keep 2 significant digits. So as our final answer, we should report 5.8 grams per milliliter. This time, instead of calculating the density or changing the units of the density, we're using this density as a relationship to convert this volume into mass. So we can convert milliliters to grams using the density. And we're going to want to use this with grams on top so that milliliters on the bottom cancel. And this gives me 93.026 grams. The numbers I have here, I only know to 3 significant digits though, so I'll go ahead and report that as 93.0 grams. This time we know the mass of some ethanol and we want to know the volume of that same amount of ethanol using density as a conversion factor. This time we need grams on the bottom so that it cancels. So I get 45.373891 milliliters, but we only knew the mass and the density to 3 significant digits. So we'll go ahead and round that down and report that as 45.4 milliliters. So for this one, we want to start with a gallon and convert it to a mass, so grams. So for the 1 gallon of gas, we are not really specifying the significant digits to start with, but this relationship has 4. So I would just kind of assume that we have 4 significant digits so that we have the milliliters in 4 significant digits. Now we have the gallons canceling and the milliliters canceling, and we get 2,834.965 grams. Even though we're assuming 4 significant digits over here, our density only is known to 3 significant digits, so we're going to have to round this to 3 significant digits and report this as about 2,830 grams. So we have one more problem that is converting from the mass, grams, into milliliters, the volume. We end up having to divide by the density so that the grams cancel. So we end up with 18.2550336 milliliters, but we only know to 3 significant digits. So we can report this as 18.3 milliliters.